for okay, for talk about the holonomic approximation lemma 1, and I would like to remind you the A principle of this H principle summer school. Therefore, do not hesitate to ask questions. Okay.
Okay, thank you. Thank you very much to the organizers for the invitation. Okay, so I want to talk about the holonomic approximation lemma. And this is going to be one of the three basic tools of the H principle that we're going to introduce in the summer school. The other two being convex integration, which Melanie will talk about, and wrinkling, which Kai will talk about. And then we'll see some more advanced stuff, but these are three of the basic tools. They're explained in this book by Yasha and Mishachev. And there's this new edition with Kai that now has wrinkling, and so you're encouraged to look at that reference. I'm going to explain things in a very slightly different way. I have some notes on my webpage from a course that I gave, and I'll give it a little bit more in that language, but it's all equivalent. So what's the idea of holonomic approximation? So, okay, suppose that I have some differential relation. And I'm going to attempt to use the same notation as Alvaro. But if I start writing random symbols on the board, that's probably because I'm reverting to some old notation, so just let me know. So if I have some fiber bundle, I don't even remember what the base was. M. Okay. If I have some fiber bundle and I have some differential relation, maybe I will call this pi. An important class of differential relations are open differential relations. Okay, and so one possible way to prove an H principle would be to start with any section and ask, can S be C0 approximated? And C0, I just mean the distance that Alvaro explained. So it's the C0 distance on the R jet space, which corresponds to the CR distance for holonomic sections. So question, can S be approximated by a holonomic section?
But then you wrote S into E, you mean there?
So I have a section can be approximated by a holonomic section that is a section of the form JR of F, or F, some actual section. Okay, if this is true, then because the differential relation is open, I win. But of course, this is not possible in general. So let's, for example, think of one jet space of functions from R to R. One jet space of functions from R to R. You can think of it in different ways. You can think of it as it's R3, but let's think of it in different ways. So there's a point in the source. There's a point in the target. And then there's a derivative. That's one way of thinking about it. You can package this in different information, which might be useful for later on. If you want, you can think of it as the cotangent bundle, which has coordinates Q and P, and then an extra Z factor. It's still the target. And suppose that I have a section that is as follows. So let's say S of Q, let's say it's Q 0. Okay. So what is, let me draw a picture. So Alvaro told us how to draw sections of a 1-jet space. I need to first draw for you the 0 order information. Remember, this is here the 0 order information, and then this is the order 1 information. So let me first draw the 0 order information. So that's just the graph of the function Q goes to Q. But then I'm imposing that it has 0 derivative everywhere. So the section looks something like this. And it now becomes clear that I cannot approximate this section, let's even say on the interval 0, 1. So you cannot approximate S, let's say over 0, 1, for example, by a holonomic section. Why? Because if I'm going to go from 0 to 1, and I'm going to go up 1 unit in height, then roughly speaking, the derivative is going to be of the order 1. And here I'm asking that it's very small. So I don't know, you can say that f of 1 minus f of 0, 1 minus 0 will have to be f prime of zeta for some zeta in 0, 1 by the mean value theorem. I always love it when you use like theorems from first year of undergrad. And so, but this is 1, okay? So you cannot have that f prime is, let's say, smaller than some epsilon everywhere. So that's the end of the talk. You can't do holonomic approximation. No. Okay, so there are some limits, but again, we just need to be aware of what the limits are, and we'll try to get around this by allowing ourselves a little bit more flexibility. Any questions so far? Yes.
Are we not allowed to vary the 0 order? Why is F1 minus F0?
It's roughly going to be, okay, so maybe not equal to 1. Let me say it's roughly going to be 1, because I want to approximate it, and here the order 1 information, this is at height 1. So, okay, so maybe f is not going to be quite there, but it's going to be within epsilon of here. And here maybe it's not going to be quite 0, but it's going to be within epsilon of 0. So, you know, maybe f is going to be something like this, and at some point it's going to have derivative 1. Or, you know, up to epsilon. More questions? Okay, so let's give ourselves some more dimension. Let's consider a similar problem in the 1-jet of functions from R2 to R2. So this again, just T star R2 times R, Q1, Q2, P1, P2, Z. And let me consider a similar section. Okay, so let's see, now I need to be a little bit careful. So I guess from this point of view, S of Q was Q0, Q. I'm just saying I've permuted the coordinates slightly different in this presentation. In this presentation, let me stick to this presentation. And so then this would be 0, 0, and let me have it go up in Q1. So draw a picture. So this section is this is the z variable. So it's going up like this. And then again, the derivatives are 0. So I want the order 1 information to be 0. Okay, so all these planes are horizontal. And so again, I cannot approximate S by a holonomic section. Okay, for the same reason, by the mean value. But what is this problem? Let's phrase this problem in a different way. This problem consists of climbing a mountain while always walking almost horizontal all the time. Okay, and this problem has a solution. Humans have known the solution for many thousands of years, and animals have known the solution for even longer. In fact, many of our highways use trails that were used by wild animals for much longer than humans walk them. So what is the solution to this problem? Well, it's the Doors' beautiful poster. You do a lot of switchbacks. Okay, and if you do a lot of switchbacks, you're able to climb a very tall mountain while all the time walking almost horizontally. What is the catch? That the approximation is not achieved on all of R2. It's achieved on some smaller subset. So let me try and write this. But you can approximate S by one jet of a function on some subset of R2U, and let me draw it. There's many possibilities, but for example, if I choose a subset, so let's try to think. What are some necessary conditions? It's the subset cannot contain any straight lines, because then I could use the mean value theorem again. So it's going to have to wiggle a lot. This U, and on top of this subset, of course, I can solve this problem just by doing a lot of switchbacks. I think so. So in this way, of course, these tangent planes are not quite horizontal, but they're epsilon close to being horizontal, and I can make the epsilon as small as I want by increasing the frequency of the switchbacks. And this is the idea of the holonomic approximation level. Okay, so the holonomic approximation lemma is nothing but a mathematical formalization of an idea that even predates humanity. So now I will attempt to formalize it, but any questions at this point? In this example, you can do it over the neighborhood of a point. Okay, so I'm about to tell you the theorem, but the spoiler is that the subset will have to be a thickening of a subset of positive codimension, maybe after some wiggling. In that case, that is the neighborhood of a wiggled line. Here, I don't really have much dimension, so positive codimension is a point, can't wiggle a point much. So in that example, I can just do it near a point. And I can do it near a point. Like here, I take a point, I take a small neighborhood, and look, here's the holonomic approximation. But not that exciting. More questions?
with the question whether sort of a section is homotopic to one, which is of the form of a jet, seems to be a bit looser and easier to answer than sort of asking.
That's right. And it's a remarkable fact that for many H principles, not only can you have these flavors of the H principle that Alvaro mentioned, but actually you can often get C0 approximation. So it's one of these things like sometimes to prove existence of a regular value, it's easier to prove that almost every value is a regular value. And here you might think that it's easier to prove just homotopic, and in some H principles that's true, but actually for a remarkably large class of differential relations for which the H principle holds, it holds in C0 dense form. But yes, it's surprising. Although, as we will see, this C0 approximation will sometimes be lost when we do things like isotoping to a core and so on. But let me not get ahead of myself. More questions? That'll be interesting. Okay. So you can be vastly more general than I'm going to be, but let me just give a definition. So a polyhedron K inside a manifold M is a subcomplex of, I won't write it, but I'll say for Sander, some smooth triangulation. Oh, I did write it. Okay, whatever. It's hard. Triangulation. I could see Sander twitching in his seat when you say that handles are the same as Morse function. But anyway, it's fine. We're mostly smooth topologists. He can deal with it. All right. So it's a subcomplex of some smooth triangulation. But you know, I'm not sure if the union of the chords of a Morse function are always the subcomplex of a smooth triangulation. But you know, any other reasonable stratified subset, I don't know, maybe Whitney stratified by smooth submanifolds is probably fine. You can be quite general, but for the purposes of today, let's just assume it's a subcomplex of a smooth triangulation. And then thing is, this board is now so horrible. I'm not sure I want to write a theorem here. Unfortunately, this is wet because I think it's been dripping. So let's see what I can do. I just want to leave this on the board, so I'm going to make it a pretty board. Okay, so then theorem lemma. Okay, I don't know. It's so let K in M be a polyhedron of positive codimension. I have some fiber bundle, and I have a section of the RZ bundle of this fiber bundle. Then there exists an isotopy of M, smooth isotopy. And there exists a holonomic section, let me just say a section on an open neighborhood of a slide wiggling by the isotopy of this polyhedron. we're here, and in what follows, A for subset A of n denotes an arbitrarily small but unspecified neighborhood of A and N, open neighborhood. My neighborhoods are always open. I know this is greatly controversial. So there exists a function like this, such that the rjet of f is C0 close to S on that wiggled neighborhood. So I achieve the approximation only on an open neighborhood of a wiggled subset of positive codimension. Yes.
Maybe the isotopy is moreover not small.
Yeah, I'm gonna put all sorts of additional remarks. Thank you. Yeah. But I just want the main statement to be clear before I start adding all kinds of strengthenings of this result. Yes.
So suppose I give you an epsilon, can you fix the isotopy and only change little f, or do you need to change both for every epsilon?
No, if you change epsilon, you will have to change the isotopy in general. Yeah, so if I were French, I would say, fix epsilon greater than 0, then there exists a Riemannian, well, we fix a Riemannian metric, yada yada, and then all the quantifiers would come before the existence of f and capital F. More questions? Okay, so now, as Gael mentioned, moreover, there's a bunch of additional stuff that I can require. So first of all, ft can be taken to be C0 close to the identity on M. If S is holonomic on a neighborhood of some closed subset, then you can take ft, the identity. I will lift this board up in a second for those in the back, and I can keep the holonomic section what it was on a neighborhood of the intersection of A and K. So this is some version of the relative form. And this also holds in parametric form and even in relative parametric form. And maybe I'll say something about this later on, but let me maybe for now not encumber the statement with additional notation until we have a good idea of why this result is true. And now I think these are all the additional comments I wanted to make. But if anyone thinks I can strengthen this result even more, then please let me know. Okay, questions? Yeah.
Sorry if you said this.
Yeah.
Can A be an arbitrary closed subset, or does it need to be a subpolyhedron or something? Or
It's fine because you see I'm always taking open neighborhoods
okay.
of it anyway, so irrelevant.
Danny?
Yeah.
Is it false if you assume, I don't know, higher regularity in one, like C1 closing or something like that?
not really sure how to interpret that. I mean, like what's higher regularity? You could think I have a section of the R+1 jet bundle, and then sure, I can replace R with R+1 and have.
No, not R. I mean in one. Moreover,
Oh, in one.
yeah.
No. This will be C1 large because you see this isotopy. This isotopy deforms this segment to this segment. So this is a C0 small isotopy, but it's a C1 large isotopy. Yeah, so. The Lipschitz constant rule. No. No.
So I have a so how does this fit into yesterday's talk? I mean, because so
Into
far,
what, sorry?
yesterday's talk.
Which one?
I don't know, like Alvarez, for example, that you
Yeah.
mentioned, like yesterday you wanted to find a solution, a section in M,
Yeah.
but now you're shrinking to something that is much smaller.
Yeah.
So how does those two worlds?
Right. So here's the plan for my 2 talks today. In the rest of today's talk, I'm going to attempt to convince you that this result is true. And in the second talk, I will deduce all kinds of H principles from it, including Smale-Hirsch immersion theory and all sorts of other good stuff.
So
How does this fit in? We will use this to prove a large class of H principles. And I agree, it's not immediately clear how to go from here to there, but that's why I'm giving a second talk.
it will happen. Okay,
Yeah,
it will happen.
It will happen. It will happen.
The section F is smooth, right?
Yeah, everything is smooth in my universe. Yeah, again. Talk to other people here, but everything is smooth. More questions? So just because I'm erasing the pictures, let me maybe draw a mini cartoon version here. So again, I have some subset of positive dimension K, and I have some section S of GRE, and I'm saying I can't approximate it on all of K, but what I can do is wiggle this K by some isotopy, and then in some very small neighborhood of this wiggled subset, here I can find some section that's holonomic and that is C0 close to S. Okay, so the first thing to do is to reduce to a local relative statement. Okay. So let me write down the proof of the local relative statement. And it's going to be the same theorem, but in Rn, and moreover, where K is standard. Okay, so more precisely, so let me suppose that I have S, a section over maybe, let's see, let I be the interval -1, 1. And suppose that I have a section over the unit cubed. Like that. And let me suppose that S is equal to 0 on near the boundary. Okay, such that S equals 0 on the boundary. This is the relative part of the statement. Then there exists an isotopy of the cube, and there exists in this case genuine function from the unit cube to Rn. Such that the rjet of this function is an arbitrarily good approximation of S on an open neighborhood of the wiggling of a subcube. And maybe I'm going to fix K and M, and K is strictly smaller than M. And moreover, I need to ensure the relative part, so let me assume that F is constant near the boundary of the cube, and F is 0 on a neighborhood of the boundary of the cube. Yeah.
It's about the last signal. So if you say that ft can be 0, the other field. If ft can be 0 small, would you not like fix the neighborhood of k and make f1 of k be in that neighborhood?
Yes,
And then effectively you're getting a solution in the neighborhood of k.
but it's not a neighborhood of K though. So, you're saying, what you're saying is true. I mean, I can have my K, and I can fix an arbitrarily small neighborhood of K, and then I can demand that the isotopy happens here. But the way the quantifiers work is I first wiggle K, and then I say that on a sufficiently small neighborhood of this wiggled neighborhood, there I can find a solution. And again, because of the mean valuing theorem, we know a priori that this neighborhood will never be able to include K. Okay, so you have to be careful with the order of quantifiers, but you cannot prove things that are false, so most of the time. More questions? Okay, so this is the heart of the argument, but let me briefly explain how to reduce from that theorem to this local statement. Okay, and so remember that K was a subcomplex of some smooth triangulation. Maybe this is K. For example. So let's prove the holonomic approximation lemma inductively using this theorem. Okay. So first of all, I can definitely construct holonomic approximations on the neighborhood of the zero simplices. Okay, so construct. You don't need any wiggling here. Okay, so suppose we've done that. So now concentrate, say, your attention on a subset U like this, and well, U is diffeomorphic to the unit Q, and here that vertex will you will be able to arrange it so that it just corresponds to a standard interval in it. And then if this holonomic approximation is, I don't know, S hat, you can think of S minus S hat. Well, jet bundles don't have a canonical vector bundle structure. They have affine bundle structures, but I can't really take these differences. But you know, over a contractible subset, I can trivialize the jet bundle. And then everything with respect to that trivialization, everything happens in the R jet of just maps from Rn to Rn. And then I do know how to take differences. So I can make this precise. And S minus S hat is almost 0 on at least near the boundary here. Okay, but I can, by shrinking the height of this cube, I might as well assume that it happens. Okay, look, I'm only interested what happens in a neighborhood of the interval, so I can change it out here without really doing too much harm. So let me just assume it's almost 0 near the boundary, and so let's actually replace it with some C0 close S tilde, such that S tilde is actually 0 on the neighborhood of the cube. And now I can hit it with this local lemma. Let me just finish the arguments and I'll go. Okay, so now use local relative statement to extend. This is kind of the key word. I'm not going to change what I've already fixed in the neighborhood of the 0 simplices. So just extend the holonomic approximation to the 1 simplices. And then you just keep going. And at the end, you're done. Okay, so proof via local relative statement. Okay, so you know, I've hidden a lot of details, but this is essentially what you do. You just work simplex by simplex, and because all of this information is locally Euclidean, that then just reduces the task to proving a statement in Euclidean space. But because I want to extend things and not ruin what I had before, I need some relative version of that local statement, which is exactly what I've written. Yes.
Can you say this a bit more precisely, how to fit those together? So you approximate the difference now by some holonomic section, and what is your new holonomic section which extends over the ones? Because you have to be careful not to do any cutoffs, right?
Not to what?
Not to do cutoff. So how do you, so what is actually the new section? Sorry.
So let's see. You replace it with C0 plus S hat such that S hat is 0. So then you use the local statement to construct some, I don't know, S hat hat. And then you will take S S hat plus S hat.
Yeah, but your S hat only exists near the zero sequence.
Your what?
Your S hat only exists near the zero sequence.
Right. You extend it in any arbitrary way, right?
That's
So simplices and extend arbitrarily elsewhere.
Arbitrarily and keeping it small, close
Yeah.
to zero.
it's not close to zero, the S hat.
I mean,
Okay, let's discuss it
how
after.
close
But,
to- how close
But here,
to S.
here I can extend it however I want. Now this local trivialization.
okay, let's discuss it after.
Okay.
Close to S.
So let's now attempt to prove this local relative statement.
But you want to see this.
Yeah, I mean, of course, yeah.
That you have that S minus S hat is almost zero or only in a part of the dependence.
Yeah, so again, I mean, look, like you have to do this with a little bit of love and care, and Kai is absolutely right, and of course you're right. But again, the point is, I don't really care what it is here, because I'm only in the end going to care about what it is in this neighborhood. So if you must, you can cut it off. The proper way to do it is to use what is called holonomic trivialization, which gives you a trivialization of any holonomic of the neighborhood of any holonomic section in the RZ space. So maybe you use that theorem with the zero order part of S. Okay, so you have to do this carefully. I'm just trying to give you the main geometric ideas. Okay. So let's attempt to prove this local relative statement in what remains. So let's do it in the case n equals 2, k equals 1, n equals 1. So ft is going to wiggle the interval I to the graph of, say, of the function x1 goes to a highly oscillating function of this form. Okay. So let's zoom in to part of it. And I'm not going to be able to construct a holonomic approximation on this whole picture, so I'm going to have to make a cut. And actually I will be able to define a holonomic approximation on the complement of that blue segment.
Sorry,
Yeah,
delta is x1 or where it's x1?
thanks. Okay, so that's that curve. So the height of this box is order delta, and the width of this box is, sorry, the height of this box is order epsilon, and the width of this box is order delta. And now, how to think? Let's also first do it in the case r equals 1. So, how to think of S? Think of S as the R jets. Okay, we'll do r equals 1 of a family of degree R polynomials, or rather think of S as a family of degree R polynomials. So a parametrized by the unit cubes. So let's say H UV W1 and W2. So now what's the game? I know how I want to build my holonomic approximation, because at every point I have this Taylor polynomial H of what it wanted to be. And so I'm just going to interpolate between the Taylor polynomials. But the problem is, if I have this Taylor polynomial here, let's suppose for simplicity, this is 0 and this is a delta, let's say 2 delta. So I have this Taylor polynomial here and I have this Taylor polynomial there. But if I just interpolate from here to here across delta, I mean, the difference is going to be O of 1, because the Taylor polynomials are O of delta apart, and this distance is delta, so that's not going to work. So instead, what I'm going to do is I'm going to interpolate between the Taylor polynomial here and the Taylor polynomial there, which are O of delta apart, over a distance, which is epsilon. Okay, and so if I choose delta and epsilon appropriately, I will be able to make the error small. So let's make this precise. Let's choose a function u like this. Okay, just monotonic, goes from 0 to 1. And then consider in that picture the box on the left, the following function, the function g of w1, w2. Well, I want it to be built by my Taylor polynomials, but I'm going to let this base point where the Taylor polynomial is base to slide from left to right as I go up. So again, we were saying let's over here it's u1 equals 0, over here it's u1 equals delta. So let me say this is h of b w2, where b of x is going to be delta u x over epsilon. Okay. So on the bottom of the box, maybe to make this a little bit better, I'll actually make it exactly -1 up to -1/2, and I will make it exactly 1 after 1/2. Okay, so on bottom of this purple box, g is equal to the Taylor polynomial on the left, and on top of the box, g is equal to the Taylor polynomial at the other end. Okay, so here, this is h0, here it is h delta, and in the middle, I'm interpolating between the two.
So that's a u2 then, or
Where?
the variable in b inside after h, the subscript b of u or b of w?
B of W2, because I wanted to change as W2 increases. As W2 increases, I want to change the base point of the Taylor polynomial to move from left to right.
Direction u2.
Hmm?
Isn't the direction u2?
The variable?
Look, what's in the name? I mean,
Well,
this is now a function.
Yeah.
Like h, I was saying, is a function of 3 variables. I want a function of 2 variables, and I'm going to feed whatever these 2 variables are into h, but I need to tell you what to do with this one. And this variable, I'm going to tell you, take W2, the height, apply this function to it, and that's what it's going to be. And it's a formula. It's a formula for a function. I had before a function of 3 variables, now I have a function of 2 variables. More questions? It might be clear, once we compute some derivatives of this function g, and you'll see, and you see what happens.
You say why h depends only on one variable, like on u, and using of s as a polynomial parameterized by one variable.
Yeah, so again, I'm only interested in what happens in the u1 coordinate. If you insist on h on being very careful, I could say that the second variable remains, let's say, 0. So I'm only interested in the Taylor polynomials along this interval I1. Okay. So I'm going to now compute some derivatives and just show that this works for appropriate choice of epsilon and delta. But you know, going back to our example, again, the point is if I try to interpolate between these two Taylor polynomials over this distance, then I'm going to create an error that's O of 1. But if I try to interpolate between these two Taylor polynomials over a much greater distance, okay, let's say this is epsilon and this is delta, then this error that I create here is O of 1, but the error that I create here is going to be O of delta over epsilon. And so as long as delta over epsilon is very small, by interpolating not in this direction, but in that direction, I can make this error as small as I want. So this is for one jet. Okay, let's be a little bit more precise and actually compute it. So you see, what happens if I take the partial of g with respect to W1? Then this is absolutely fine because this is just going to be the partial of h with respect to W1 at the point B of W1, 0, evaluated at W1, W2. And that is going to be very close to the partial of h with respect to W1 at the point, let's say, W1, W2. I got which is the value of s, or the which is the corresponding component of s. Why? Because this point is C0 close to the point W1, W2. And therefore, by continuity, if this point is close to this point, this partial is close to this partial. So this term is completely fine. It's the other term that's more interesting. So let's see what happens if I compute the other derivative. If I compute the other derivative, well, I need to hit it in two places. There's one place where I hit it, and it's just like before. And this term is fine. This is close to the partial that I want it to be. Because this point is close to the corresponding point. This is all in this box. Okay, this is all happening in that box. But then there's another term, which by the chain rule corresponds to B prime of W2 times partial of H with respect to U1, okay, at the point BW2 0, evaluated at W1, W2. This is the error term. But you see, this whole thing is, whatever it is, it's a continuous function. So it's a priori bounded by some constant. And this term B prime, what is it? Well, again, by the chain rule, it's delta over epsilon U prime W2 over epsilon. So that is bounded by delta over epsilon times some constant. And so what's the conclusion from that calculation? That if delta over epsilon is very, very small, then the one jet of this function g is C0 close to S. And more generally, you can convince yourself that if you pick delta and epsilon so that delta over epsilon to the r is sufficiently small, then a similar calculation of partial derivatives will tell you that the r jet is to the order 1 part of S. And that's essentially the whole proof in that in the special case k equals 1, m equals 2, n equals 1, r equals 1. So I want to finish with some final words about the general case, but I know that I've said a lot, so let me just pause and allow you to look at that calculation, and I'll try to wrap up right away. Any questions or anything useful that I can say?
Maybe. In the picture that you drew on the right board,
Yeah.
it looks like you want both delta and epsilon to be small, right?
Yes, both delta and epsilon will be very small, but what's important is that you choose delta and epsilon small, so that delta over epsilon is also very small.
Okay.
Where did you use F1? Capital F1.
Capital F1, so you see, if I do this, I can do this over all of these blocks. And each time I mean, you can do this in different ways, but each time I have to remove some segment like so. And on the complement of these segments, you can define G. And so, okay, so then you just need to find a wiggling of the interval that avoids these segments. And so I proposed a concrete one that's sinusoidal, but you know, you can pick any one you want. So so you define G on complement of the cuts, and then choose Ft so that F1 of I avoids the cuts.
But it's only for the shape. I mean, you're not using the analytical expression that you're.
No, it's just so that it avoids those cuts. Because you know, I can define a G in a similar way over each of these, and then it glues, so that's it.
Exactly. Okay. So it should be a delta minus 1 maybe in the sign.
Maybe. Any more questions? Okay, so then just to end, and then you know we can entertain Kai's objection and whatever other questions you might have, but just to conclude, because there is one more step. Suppose that now you try to implement this in more in more dimensions. Let's say now I have x1, x2, and x3. I can perform this scheme treating, let's say, x2 as a parameter, and maybe cutting things off near the boundary of the parameter space and do the wiggling in the x1 direction. And then you will make a section that is holonomic with respect to the first variable x1. Okay, but because you just do the same thing parametrically with x2 as a parameter. Okay, and then you do the same thing now with respect to the other parameter. So you will then now further wiggle in the x2 direction, and so you will have this family of sinusoidal curves that itself oscillates sinusoidally in the parameter direction, a little bit like a swimming pool. And then on a wiggled neighborhood of this subset, you will be now able to construct a holonomic approximation. And in general, if you have arbitrarily many directions, you will have to repeat this process with as many directions as you have, and then at the end of the day, you win. So anyway, that's the end of the talk.
Okay.